Good morning, everyone. Thank you all for coming. I'm going to share with you the highlights reel from a project, an NSF-funded project to assess the thermal tolerance of all of the planktonic larval stages of the lobster. I have presented this work in a couple other venues, so I know there's a lot of people in here like Ben and Jason and Lydia who are going to view this as rehash or maybe even tri-hash, possibly quadra-hash. But in the spirit of collaboration, I do want to acknowledge that this was a collaborative effort between Hood College, Bigelow Laboratories, the Department of Marine Resources, and University of New England. And everybody contributed to this in a way that made it possible for it to happen. No one was shirking their duties. So these are my co-authors on the talk, and here we go. So I'm going to start with the take-home messages in case you fall asleep, and you can come back later. What we see in terms of vertical distribution of both the stages, like 1 through 3 that are up in the water column, and then stage 4 as they settle on the bottom, is consistent with their range of thermal tolerance. So that's cool. Cold bottom temperatures do appear to limit deep water settlement based on what we've seen in the field. And behavioral responses to temperature don't necessarily align with the physiological limits of their temperature tolerance. So things aren't going right up to their critical temperature and facing death. They are reacting to temperature before they reach their critical temperature. So to that end, sublethal effects are probably driving a lot of the vertical distributions that we see in the field. Our approach to this was to really have a research arc that started with the physiology of individual larvae and basically link that to distributions and both vertical and settlement wise in the field on the scale of meters to kilometers. So let's start with the physiology. One of our primary tools for this was respirometry and measuring scope for activity or aerobic scope. We use them a little bit interchangeably. The caveat on scope for activity is that there's probably some anaerobic metabolism in these experiments that we are not keeping track of. Excuse me. But basically what we do is we put individual larvae in respirometry chambers and we measure how much oxygen they consume when they're swimming actively or when they're just resting on the bottom. And the difference between those two gives you aerobic scope. The more aerobic scope you have, the more metabolic bandwidth you have to deal with temperature stress. As that number approaches 0 at the stressful temperatures, that's when you're reaching the critical temperature for the organism. We bolstered this with some survival and growth experiments that were longer term experiments, chronic exposures to temperature. We looked at gene expression using transcriptomics. And then we ultimately related this to what was happening in the field by comparing our physiological data with the vertical distribution of stage 1 through 3 in the field. And then we looked at settlement as a function of depth and temperature. And then finally, to really link the physiology of the individuals with what's happening in the field, we actually put larvae in cages and deployed them at different depths so they'd be exposed to different temperatures in the field and looked at growth and survivorship. These are the functional response curves for aerobic scope as a function of temperature for the 4 planktonic stages of the larvae. The vertical blue lines indicate on the bottom indicate the low critical temperature, and the red indicates the high critical temperature, which is where they intersect the 0 aerobic scope, which is the red dotted line through the middle. So what we found was that stage 1 was the most cold tolerant, had critical temperature of somewhere between 6 and 28 degrees. This makes sense. They've just spent the winter overwintering on the bottom. There's probably a lot of cold acclimation that's gone on there. As they molt into stage 2 and then into stage 3, we see that their cold tolerance is diminished and their tolerance of heat stress increases. When you get to the stage 4 larvae, you have a little bit of an increase in cold tolerance, but more importantly, this is the narrowest thermal range of them all. And we speculate that this might have something to do with the fact that this stage is heavily calcified and they are active swimmers and they're probably putting a lot more energy into maintaining their position in the water column, probably don't have as much energy left to deal with thermal stress. It also probably makes them the most vulnerable stage in terms of climate change. Now, to try to apply what I just showed you in terms of the aerobic scope and the physiology to the field distribution, we had to dig into an old data set from Harding et al. 1987. Why are we using a 40-year-old data set? Because nothing contemporary exists. But what we did was we took those functional response curves and we took the temperature profile that Harding et al. Reported, and we used that temperature to estimate how much scope would be available to the larvae as a function of depth. So what you see on, the shaded part doesn't show up very well here. This portion, this curve that you see over here, everything over here is supposed to be shaded. And what that represents is the percentage of their maximum potential aerobic scope that they would achieve as a function of temperature at any particular depth. The dots that you see and these wavy lines are the distribution in night and day of the different stages of lobster larvae as Harding reported in that paper. And what you can see is basically the stage ones have a huge proportion of their aerobic scope available to them throughout the water column. As you molt to stage two, they lose a lot of their capacity for aerobic scope at depth. And it's even slimmer in the stage threes. And so I think what this represents is basically physiologically, it's really not good for the stage twos and threes to be down as deep as the stage ones. And so you see their distribution start to shoal as this available aerobic scope shoals with them. An important aspect of this is that in this temperature profile that they reported, all of the temperatures are at or above the critical temperatures that we determined for these larval stages. So that means that if this is a contributing factor to their vertical position in the water, they're responding to a temperature that is not quite the critical temperature. They're responding to something that's warmer than that, that's keeping them higher in the water column. Is that the only thing? No, of course not. There's some evidence for diel vertical migration in Harding's data. They could be following light levels, prey, avoiding predators. These are all things that are really important. All we are trying to say is that they are staying within a physiological comfort zone for them as they make these vertical migrations, and it changes onto genetically. I'm really pleased we actually just found out 2 days ago that this has been accepted by marine biology. So look for that coming to theaters near you. Just a quick aside. One of the undergraduates that worked on the project, Julie Carlson, did this really cool project looking at cardiac function as a function of temperature. And what she did was she glued larvae in place, and we had a setup with a water bath that she could rotate her experimental organisms through, and we'd hold them at different temperatures, and she took video of their heartbeat, which you can see through the carapace on kind of the posterior edge of the carapace is where the heart is. So she was able to document heart rate from the video analysis, which increased with temperature, which is what you would expect. But the really interesting thing was that she was able to use these images to calculate the volume of the stroke of the heartbeat. And so if you look at stroke volume, how much blood is actually pumped with each beat, it drops a little bit at low temperatures, but it drops a lot at high temperatures. So when that heart rate is beating really fast, it's not getting a full contraction. You multiply heart rate times stroke volume, and you get the cardiac output in, what is it, microliters per minute. And what's really interesting about this is it drops off at both the low and the high stressful temperatures. And this fits in really nicely with the oxygen capacity limited thermal tolerance hypothesis, which posits that basically an organism's thermal tolerance is defined by an inability to perfuse its tissues with oxygen adequately at both high and low temperatures. And from the low end, it's a mechanistic thing. And from the high end, it looks like it's a mechanistic thing too because of the stroke volume. This doesn't account for differences in oxygen saturation, but nonetheless, this is kind of a cool mechanistic underpinning for for what we're seeing in terms of thermal tolerance. A lot of you have seen me pitch this. We got this published earlier this year. This is a caveat. One of the caveats for what I've shown you so far with the thermal tolerance of the various stages is that we did all of that with lab-reared larvae. What we found out in the course of this study was that wild larvae, which are superior in many ways, are also much more tolerant of heat stress. And so if you look at their physiological response to heat stress in terms of aerobic scope, you've got about a 4 or 5 degree difference in their tolerance of thermal stress at both the cold and the warm levels. So this means that we need to do more to figure out how to raise larvae in lab that are comparable to their field counterparts, or we've got to find a way to catch more of those 1, 2s, and 3s in the field in a way that we can actually get them back to the lab and do some experiments on them. In other words, I just undermined the entire premise of all of my work. One thing that was kind of interesting, this was work that Aubrey Jane did, a graduate student on the project, who quite honestly, this project never would have happened, or at least wouldn't have been successful without her efforts. But she looked at transcription, and one of the interesting things underpinning this difference between wild and laboratory reared larvae is you see in response to low temperature stress, the lab-reared larvae are upregulating a whole lot of genes, and a lot of them are related to cold stress. The wild larvae are upregulating very few. Similarly, at hot temperatures, you've got wild larvae are upregulating some, but the lab-reared ones are upregulating a lot more. So this is really taking it down to the molecular physiology of the organism. So what's it all mean? Well, we went out into the field to try and link these things. As I said, we measured settlement, we used collectors, never again. We also built these cages that we could put individual wild-caught stage 4 larvae in, and we deployed those at depths of 10, 40, and 80 meters. We did anecdotally note that we had better returns and lost less gear if it had a smiley face drawn on the buoy. Who's going to cut gear that has a smiley face on it? Settlement was everything we expected we would find based on everything that Rick Wally started back in 2013 and ALSI has seen since, is that, hey, settlement decreased with depth. Thank God that happened, because otherwise we'd have to explain a lot of stuff. We actually, down at our deepest settlement sites, we only got one settler in all the collectors we had down there. Much higher settlement in the shallows. This was not a function of larval delivery. We did noosed on tows over these sites. Did not correlate. It was also does not appear to be a function of predation because the predators actually follow a similar distribution. When you look at it as a function of temperature, our only really high settlement occurred above 12 degrees. So this may present a threshold for settlement in deeper, colder water. Settlement does occur, but not nearly in the abundance. You get about 3.5 times the amount of settlement occurring above 12 degrees. In terms of the ones that we deployed, there's definitely sublethal effects. In the shallows, they get larger in the 8-week deployment. Their molt percent increase is significantly higher than the deeper ones. And the shallow sites were the only ones that were above 12 degrees. Part of this is that they don't grow as big in colder temperatures. So this is laboratory data that we have. But part of it is that in this case with the percent increase is that I think a lot of those individuals actually molted twice in the shallow water. So there's a distinctive sublethal effect. We saw very little mortality at all in any of these depths. So they can live down there, but it's not advantageous. So let's tie it all together in my last 40 seconds. The behavioral response to temperature doesn't appear to align with the physiological limits. We know from work that I did as a graduate student back at the turn of the century that if you get in the water and follow them, they don't spend any time below 12 degrees. In terms of settlement, we see that they're predominantly settling above 12 degrees, probably restricted by a behavioral response to temperature. And it seems like this is probably driven by sublethal effects rather than an actual, they go below 12 degrees and die. In terms of how we think about how the organisms respond to temperature, shut up. How they respond to temperature, I would encourage people to think of this not so much as what critical temperatures are driving distributions in the field, but something like Page's temperatures, which Page's temperatures really reflect when things are turning worse for the organism metabolically. And so I would argue that 12 degrees is probably a low Page's temperature for the stage 4 larvae, and that's why behaviorally they respond well before they're reaching their critical temperatures. We held stage 4s at 3.5 degrees for months without them dying, the wild ones. And so they can tolerate the temperatures, but they avoid them. I've been cut off. Shout out to the lobster larvae survey in Booth Bay. That's where a lot of our larvae came from. This was a labor-intensive project. We raised our larvae individually in jars. We maxed out at a little over 1,000 in the system at once, and they all had to be changed and fed 3 times a week. Like I said, I'm never doing collectors again because that's how you fill them and get them ready to go to the water. So a big shout out to all the students that were part of this project. And finally, a shout out to my son who we started this project in COVID and he helped, we set up a lab in my basement in Maryland and Jess Waller from DMR shipped me live larvae and we started doing experiments and he helped maintain the larvae in our basement. So with that, I would be happy to take any questions.
I always have a question. Great talk. That was new for me, so I really enjoyed it.
Thank goodness, somebody I reached.
I have 2 questions. One, what percentage of max orbit scope did you use to define your Page's temperatures?
We kind of reverse engineered this because Page's temperatures are, if you look in the literature,
Not
really
well defined.
difficult to define. Yeah. No, there's no set like percentage that's out there in the literature. So what we did, this is how we circularly reinforce our support for our hypothesis, but we looked at this avoidance of 12 degrees and said, what is the aerobic scope at 12 degrees? It was about 80%. And so then we applied 80% universally across all of the stages. So that is another caveat, which is that if we look more closely at more realistic wild caught larvae, we may need to move these Page's temperatures around some. Cool. But this is a starting point.
Yeah, totally makes sense. My second question is related to your heart rate and the OCLTT. So when you found that really nice curve for cardiac output, but they were on stage 1 lobsters, correct?
Yes.
How much of their oxygen uptake is actually due to the circulatory system or the cardiorespiratory system versus being absorbed passively through the cuticle?
That's a good question. I will start by saying that actually we did this with all 4 stages and we get very similar results, but the prettiest ones were in stage 1. So that's what I put in the presentation. I don't know what the contribution could be just diffusively through the shell. That would be a really interesting component to add to this. I think what we really need is also that would be helpful is if somehow we could get hemolymph out of something this small and see what the actual oxygen concentration is in their blood as well. Cool. So somebody needs some micro technique development is all I'm saying.
Yeah. And then finally, really quick, did you look at the Arrhenius breakpoint temperature on heart rate and does that correlate with your Page's temperatures?
We didn't, and in part because like we took them up almost to a lethal threshold, but we didn't get the part where the curve starts to come down. So we haven't done that analysis, but we probably should. Okay, cool. We'll talk. This one's in prep, so we haven't got to that yet. Rick.
Eric, really nice talk. And notwithstanding your aversion to collectors, my feelings aren't hurt. And you did get some really great data from them. So that's great. But my question comes back to your conundrum about why lab-reared lobster larvae with great food supply and so forth just don't get as big. And what are your thoughts? And do you think that
Where's Alex?
The big ones that you see in the field are just the survivors of what may be
I think
greater range.
selective survivorship is definitely one possibility. We did a couple of different trials where we reared them with different methods. We reared them at colder temperatures, and just based on acclimation, they came out a little more cold tolerant, but they still didn't have the heat tolerance that the wild ones had. We fed them a natural diet of copepods, and we got ones that were significantly larger than the brine shrimp fed ones in labs. So I think diet is huge. And there are a bunch of essential fatty acids that they get from their natural food sources that they don't get from brine shrimp, that particularly at the cold end, those fatty acids help maintain membrane fluidity at low temperatures. And so diet is probably huge. Alex and I have had conversations about this. So I think, if we want to raise better ones in lab, we need to come up with a diet. That's like the primary focus area.